chapter 1, right? And we're going to start with interval notation, which we've kind of already seen. But quickly, let's do some examples here. So if I have, the interval from -2 to 12, another way to write that is -2 to 12 with closed brackets because it's less, it's closed circles, right? And then if I have x is less than -17, it's all the numbers less than -17. I'm sorry, x is greater than -17, starts at -17 and goes up. So it's -17 to positive infinity. I have to have an open parenthesis, not a bracket there, because that's an open circle, greater than. The infinities, I don't know where infinity is, right? It's not a point that I can go land on. So infinities always get open parentheses. Here I have x is less than 3. So it's all the numbers from -3 to negative infinity to 3. And these both are open parentheses. We say it's an open interval. Or, right, when you have the word or, it translates to this capital, curved U. X is greater than or equal to 8. That's all the numbers starting at 8 and going to positive infinity, but like this. Okay? X is less than 0, negative infinity to 0, open. Yeah. You don't have to. I often leave it out, but the negative you obviously should. Okay. So, yeah.
So, wait, if you go up for you said the infinity has to be closed, or has to be an open, like parentheses, but what would you put the bracket in front of the -17?
No, because this is also an open circle, right? Less than versus greater than versus greater than or equal to. Yeah. Okay, so let's talk about functions. Functions are basically like a mechanism that you give it an input and it comes out as an output, right? And so it produces a set of ordered pairs, okay? For it to be a function, no two pairs should have the same x value, okay? So each x value should have a different y value. So to see whether or not something is a function, there are several things we can do. One is, if you have the graph of it, you can do the vertical line test, which means you draw a series of imaginary vertical lines through a graph. And the condition is each vertical line should only pass through one point on the graph. Okay? That means it passed the vertical line test, so it's a function. All right, so and then some other ways that you can determine whether or not a relation is a function is the following. If you're given coordinate points, go through the coordinate points and make sure no x's repeat. So here, none of the x's repeat. So yes, this is a function. Here, look at this one. Same thing. Do any of the x's repeat? Yes, the x's repeat here. Now you just have to make sure that for the repeating x's, if you have different y's, then it doesn't work. So you see here how you have 2 with a 0 and 2 with a 5. That doesn't work. So no, it's not a function. Okay? What about the next one? Is the next one a function? Do the vertical line. Because each vertical line passes through one point of this, yes, it's a function. Okay, take a look at this, right? Take a look at this. So the condition is for every x value, you can only have one y value, right? Okay, so here you have an x value here. what happens if you solve this for y? Well, you get x over 2 is y squared. Take a square root, take a square root. Y is plus or minus root x over 2. What that means is, suppose x equals 5, right? Then what does y equal? Y would equal positive root x over 2 and negative root x over 2. Because y can equal two different x values at the same time, it is not a function. Okay? All right. So that takes us to function notation. Function notation looks like this, right? And we read that as f of x. Okay? So when you have f of x, f is the name of the function. X is the variable in the function. Okay? When you have your function, the x variable represents the values in the domain of f, and it's called the independent variable. Y represents the range of f and is the dependent variable. Okay? So let's practice a little with function notation. Here we go. For each function here, we have to find two things. We have to find f of a and this. Remember that? F of a plus h minus f of a? We saw that in the trig chapters as well. All right. So, okay, so first, let's find f of a. Well, if f of x is this, and I need to find f of a, what has happened here? X has been replaced by a. So what does that give me? A squared minus 2a, right? F of a is a squared minus 2a. We're replacing the x with the a. Okay? Now, next, I want to find f of a plus h minus f of a over h. Okay, this is like a recipe. It's like a script. It calls for certain things to build this. The first thing it calls for is f of a, which I've already found here. Okay? The next thing it calls for is f of a plus h. F of a plus h. Well, what is f of a plus h? Let's see. This is f of a, right? What's f of 2? Right, just going along with it. What would f of 2 be?
2 plus 8.
Well, here, if this is f of x, what's f of 2? 2 squared minus
4.
2 squared minus 2 times 2, right? Basically, you're substituting this for all the x's. So now if I have f of a plus h, now I'm substituting a plus h for each of the x's. That means it's going to be a plus h squared minus 2a plus h. Okay? So look, f of x. Every single x gets replaced by a plus h. I have an x here, gets replaced by a plus h. I have an x here, same thing. Okay? Does that make sense? So now let's simplify this. This is a squared plus 2ah plus h squared minus 2a minus 2h. Okay, now let's build our function here. Okay? First, the red part is what I just found. Okay? Minus f of a. F of a was a squared minus 2a all over h. Oh, sorry. Parentheses. Okay? Okay, so now I need to simplify this. You distribute this, but I don't want to make you guys like write the whole thing over again. So that's just going to be negative a squared plus 2a. So let's see what happens now. A squared minus a squared goes away. Negative 2a positive 2a goes away. So what I have left is 2ah plus h squared minus 2h all over h. Okay? Can I factor out an h from here? All over h. Look, the h's go away. 2a plus h minus 2 is what I have left. Okay? All right. So next, what do I have next? Next, I have a completely different function. F of x is equal to 3. Well, let's see what that looks like. F of x is equal to 3. When I graph it, that's like y equals 3. One, two, three. That's what that looks like. Okay? Now, I need to find f of a. Okay, well, let's see about this. When x is 0, what's y for this function? 3. So f of 0 is 3. When x is 1, what's y? 3. So f of 1 is 3, right?
So anything of f equals 3.
Right, so what's f of negative 7?
3.
3. So what's f of a?
3.
3. Okay? So then, okay, so that's the first one. So now number 2, we're going to do f of a plus h minus f of a over h. So then if f of a is 3, what's f of a plus h?
Or is it not 6? Sorry.
Is it 6? Okay, so suppose here is a. A plus h is somewhere further down the line, right? What's the y value there? 3. So that's also 3 over h. 0 over h, 0. Okay, yeah. All right. So that's function notation. Let's do a little bit about domain. Okay, if you're not explicitly told what the domain for a function is, then there is an implied domain, which is all of the x values for which the function is defined or real. Okay? So, all the real numbers for which the expression is real. Okay? Now, how do you find the domain then? You look for the values of x for which the function is undefined. You exclude those, and whatever is left, that's the domain. All right? So you have to exclude values from the domain of a function that would result in dividing by 0 or taking the even root of a negative number, right? So there are, like, when can the function not be defined, or when can it be not real? Well, either when you're dividing by 0 or when you have to take the root of a negative number. Okay, so as long as none of those things are happening, then that's the domain. So take a look at this one. Yeah. Zero. It's zero. Right. Okay, so hang on. So here, when would we have a problem for this first function? When x is -2, right? So x shouldn't be -2. Okay? Well, what does that mean? If you have a number line and this is -2, -2 is a bad point for this function. But all the other points work. So for example, everything from -infinity to -2 is good. So here, these should have parentheses. -infinity from -2 is good. And also, everything from -2 to +infinity is good. So that's the domain. Right? So we excluded the bad point and we took the rest. Here, we want the integrand, the radicand, the stuff inside the radical, to be positive. So I want x minus 2 to be greater than or equal to 0, which means x has to be greater than or equal to 2. So the domain is all the numbers starting at 2 and going to infinity. Okay, so we're going to do lots of examples right now on this. Yeah.
Again, 2, if square root of 0 is just 0.
Right, so 2 works. We're saying 2 works because you get root.
Oh, I thought we were saying that 2 doesn't work.
No. It's all the numbers from 2 to +infinity work for this.
Oh, I
yeah.
Backwards.
Yeah.
Okay, I got it.
Okay, so we're going to split up all the functions into 3 different categories. 1, polynomial functions. Polynomial functions are functions where variable has whole number exponents. Whole number meaning 0, 1, 2, 3, 4, okay? So any of these basically. So here we go. For polynomial functions, the domain is always all real numbers. That's it. Okay? So take a look. This is a polynomial function. Any value of x works in this equation. So the domain is all real numbers. Same with that one. The domain is all real numbers. Okay. Yeah, real quick. I want you guys to use this notation. Yeah? Okay. So, all right, next we come to rational functions. These are like the ones with the denominator. Okay? The domain is every number except the zeros of the denominator. So basically, here's what you do. Set the denominator equal to 0. Get those x values, exclude them, and the rest are good. Okay? So, this first one, I'm going to factor. Okay? So I take that denominator, set it equal to 0. So I get x equals -4 and x equals 3. Okay? Those are the numbers where this denominator is 0. This means x cannot equal -4. X cannot equal 3. So if you look on a number line, it can't be -4 and it can't be 3. So what can it equal? Negative infinity to negative 4. Union, that's the union symbol. Negative 4 to negative 3. Negative 3 to infinity. Right? Yeah.
I thought for when you have a problem like this, can't you write just the domain is like all the numbers but not these two?
You can, but we're using this notation, in which case, you know, this is how you need to write it. Right, we're getting ready for upper level math now. Yeah.
Oh, I think it's supposed to be 3. Am I wrong?
Oh, yes, it is supposed to be
Okay,
3.
no,
Sorry.
No, you're good. I just wanted to make sure I was.
Yep. Okay, good. Okay, next one. Look at the denominator. Can't equal 0. So t can't equal plus or minus 1. Okay? So, but it's, you know, all the numbers other than that. So domain is negative infinity to negative 1, negative 1 to 1, 1 to infinity. Okay? All right, next one. So when you have ones like this, you have to set each of the denominators equal to 0. Right? Why? Because if you were to do a common denominator, what would the common denominator be? It would be x plus 8 times x minus 10. Okay, so again, you know, each one of them set it equal to 0. So x can't be negative 8 or 10. So the domain is negative infinity to negative 8, negative 8 to 10, 10 to infinity. All right. So the next one is a little bit more exciting, because let's take that denominator and let's set it equal to 0. Well, that can't factor. So x squared is equal to negative 1. And right there, you might be able to see it. And you're like, wait a minute, you can't square something and equal a negative number. But let's say you don't see it right then, you know, because, you know, you just move on mechanically, take a square root. Well, x is plus or minus I, right? Well, that means there is no real number for which the denominator is 0. There is no number for which the denominator is 0. And if the denominator is never 0, then we don't have a problem. So the domain is all real numbers. Okay? So here we go. There is no value. So the denominator is never equal to 0, which means there are no problems. There are no numbers which give us an issue. So the domain is all real numbers. Okay? All right. So we did polynomial functions, rational functions. Next, radical functions. Okay? Radicals. Right, so we can have two types of radicals, either even or odd roots, right? An even root, it's like if you have the square root of x, 4th root of x, and so on, right? Well, the thing with even roots is the radicand, the stuff inside, has to be greater than or equal to 0. Okay? But if you have an odd root, cube root of x, 5th root of x, it's all good. Can you take the cube root of negative 8? What's the cube root of negative 8? Negative 2. Like that totally works. What's the cube root of positive 8? Positive 2. So it doesn't matter. So for odd roots, the domain is all real numbers. Okay? Okay. So, here we go. Even root. Set it equal to, it has to be greater than or equal to 0. 7x greater than or equal to 70. X is greater than or equal to 10. Okay? Okay. So what's the domain then? 10 to infinity. Okay, let me do the next two and then I'm going to go back to B. What's the domain here? All real numbers. Okay. Take a look at this one. Let's rewrite this as square root of 9x minus 2 cubed. At the end of the day, this is an even root. So the stuff inside has to be greater than or equal to 0. 9x greater than or equal to 2. So x is greater than or equal to 2 over 9. So what's the domain? 2 over 9 to infinity. Yep. Oh, so if you did, you would just take the cube root of both sides and it goes away. Yeah. Okay, let's go back to this one. Okay, so we want the integrand to be greater than or equal to 0. You know what the difference is between this and the other two? Is that here, like when the cube root went away, also in D and in A, we had a linear expression greater than or equal to 0. So those two, B and D, ended up being linear inequalities. For B, it's a non-linear inequality. It's a quadratic function. So the process is a little bit different. And you're going to go back to Algebra 2 and think about this. So it's x minus 5, x plus 3 when we graph this, greater than or equal to 0. All right? So remember what you did with that in Algebra 2? You get that, x is 5 here and x is negative 3. And then you put it on a number line. Do you remember that? Yeah? Okay, so, so now we get values from each of these, and we're going to plug them into these parentheses. So if I pick negative 10, plug it into the first parenthesis, that's a negative value. Plug it into the second one, that's another negative value. Their product is positive. From the second region, if I pick 0, plug it into the first parenthesis, you get negative, positive, negative. And if I pick a larger number than 5, like 10, positive, positive, positive. Okay. I want the values of x which make the integrand positive. That's this region and this region. So how do I write that? Negative infinity to negative 3 and 5 to infinity. Yeah. Okay, so put negative 5 in here. What do you get? Negative 10 times negative 2, positive. If you put negative 5 in here, you get... Yeah.
I gotcha.
Okay. Thank you. Now take a look at the next one. The next one has real issues. Not only is there an integral, I keep saying integral. Not only is there a radical, but it's in the denominator. So the thing with the radical is x plus 2 should be greater than or equal to 0. But since it's in the denominator, can it equal 0? No. So it should be only greater than 0. All right? So x is greater than negative 2, which means the domain is negative 2 to infinity. Okay? And we did that because it's in the denominator. There are 2 restrictions on us. Okay, next one. All right. Look at the numerator. That's an integral. Oh my God, I keep saying integral. That's a calculus term. That's a radical. Okay, that's a radical. So the first condition is x minus 3 has to be greater than or equal to 0. So x has to be greater than or equal to 3. Okay? So what numbers can x equal so far? 3, 4, 5, 6, 7, 8, okay, and everything in between, yeah? Okay. The denominator tells me the denominator can't be 0, so x can't be 6. So now I've got some conflicting information. One is telling me it could be 3, 4, 5, 6, 7. The other one's telling me, it can't be 6. So let's just see what it is that we're looking at here. Okay, let's just draw a number line for ourselves, because once we put everything on a, once we make everything visual, then it's so much easier, right? So what's the blue deal telling us? This, okay? What's the red guy telling us? This. So what numbers are okay? 3 is okay. 4 is okay. 5.9 is okay. 6 is not. 6.1 and everything else, those are okay. So the way I'm going to write that is the numbers from 3, including 3, to 6, but not including 6 are okay. And then after 6 to infinity are okay. Do you see what a convenient way, right, that is of writing that, right? Sorry, I just need to reduce some of this clutter. It's making me antsy. All right? Okay, G we're going to skip because it's a repeat of one before. Yes?
So when you put it like that, the answer, right? So when you set it to 3 and 6, right? So 6 isn't included?
It's not included because it goes right up to 6, like 5.9999999.
But it's not included. You still have to put 6.
Yeah,
Even
because
if it's not included.
right, because you can't put 5 because then you're leaving out 5 to 6. Yeah. Okay. All right. Look at this one. The numerator here, not a problem. The denominator, problem. What am I going to do? 2x minus 3, what? Greater than 0. So x is greater than 3 over 2. So it's 3 over 2 to infinity. Okay? That's the speed version of that. Okay.
Oh, no, that can equal 0.
X minus 5 can equal any number. In the numerator, it can equal, there are no restrictions. Okay.
But you wouldn't never.
All right. Let's go to piecewise functions. Okay. So I know you did piecewise functions in Algebra 2. We're going to repeat, do it very, very practically. Okay, take a very practical approach to graphing these. You cannot move on from pre-calc to calculus, any form of calculus, without being an expert on piecewise functions because it's just everywhere. So let's go. The thing about a piecewise function is that the function contains 2 different equations that are graphed on separate intervals. It's like 2 functions are roommates of each other, right? And they've split up the house. This is my domain. Literally, that is your domain. Right? You like that, huh? Yeah. Okay? So now, what tells you how the divisions have occurred? That's these two. So we have two functions here, and I'm going to color code them. We're not talking about what the functions are yet, but one function just lives in the space where x is less than 0. Just this space. The other function lives in the space where x is greater than or equal to 0. Okay? So that's where they live. That's how they've partitioned the living quarters. Now, let's see who lives where, how we're going to do it. In the blue zone, we're going to graph this function. In the red zone, the other function. Okay? Now, what you're going to do is you're going to make a chart. Okay? You're going to pick values for x. The first value you're going to pick is always going to be the end point. Where is the end point? 0. It's where the partition occurs. So 0, that's the end point. When x is 0, I plug it into that blue equation. I get negative 0 plus 2, 2. So when x is 0, y is 2. And because at that partition I have an open circle, I put an open circle there. So far, so good, right? Pretty innocent. And it stays that way, really. So now let's look at, because we're now pre-calc students and we're more like woke than we were last year, let's look at what it is that we're graphing there. We're graphing negative x plus 2. Envision negative x plus 2. What kind of a graph is that? A line going downward, yes, with a slope of negative 1. So that's what you have to graph there. Some people look at it and they're like, okay, Miss Malika, I get it. Like you just draw a line there with a slope of 1. Fine, do that. Good, perfect. Some students are like, okay, I'm lost. And then you're like, okay, let's pick another point. Okay, so now can I pick x equals 3? No, because it's not in the domain, right? Can I pick x equals negative 2? Yes. Yeah. Put it in there. Negative 2 plus 2, 4. When x is negative 2, y is 4. That's just a dot, right? There is no open or closed circle business there. So look. That's how that looks. Okay? So I'm done with that. Yeah.
2 questions. One, do you need to put an arrow at the end?
No, you can, but I don't require you to.
And second, do you need to draw that table to graph a symbol or a more simple function like that?
No, but make sure, if you're going to do it mentally, make sure you are absolutely, plotting this point on the partition. Next, next we need to do the red graph now on the other side. So let's draw x and y again. Let's do the chart again. First is the partition, 0. I'm now going to put it in here. 0 squared plus 2, 2. When x is 0, y is 2. Oh, look, it coincides with that point. But is it an open or a closed circle there? Okay, if it's open, unclosed, when they overlap, just fill in the circle. Okay? That's it. No, just close the circle. Now, what shape is it that we're graphing there? It's a parabola, right? Okay, so let's just pick another point. Let's pick 2 this time. 2 squared plus 2, that's 6. When x is 2, y is 6. But remember, it's got to be a parabola. Look, I just graphed my piecewise function. Okay? So listen. This is precise enough for our purposes. Okay? It's got the shape of a parabola. We are good to go. Okay? All right. So do you see how methodical we were and how practical an approach we took? And it was innocent and, no tears were shed, right? I find when students come to pre-calc after algebra 2, they're like, oh my God, piecewise functions. But they're really not that bad, okay? All right, I'm going to move on to example number 8. Let's graph another one. Okay. I have 3 regions here, which is fine. Yeah. We're going to skip that other one. We're just going to move on to here. We have 3 here, which is fine. So first it says to find f of negative 2. Okay, x is negative 2 here. Of these 3 regions, where does negative 2 fall in? First, second, or third? First. So that means because it falls in the first equation, I say f of negative 2 is negative 2, positive 2. What about f of 3? Which region does 3 fall in? The third. So that's the third equation, which is just what? It's just, well, the function is 1. So f of 3 is 1, just like the y equals 3 on top. So f of 3 is 1. Okay. Let's graph. I have 3 functions now. That's number 3. I'm going to color code again, 1 and 2. Okay? All right. So to graph equation 1, let's do x and y. What point do I put in here? The end point, what is it? 0. And so y is also 0. Open or closed? Huh? Open. And look, this is negative x. It's basically a line sloping down with a -1 slope, right? So if you can figure out that that's what that looks like, please, this is Precalc Honors. I want you to be, able to do that. If not, plug in another point. Okay? All right, number 2. Okay, look at number 2. Number 2 has how many endpoints? 2 endpoints. You're going to plug in both endpoints. Both endpoints. When x is 0, 0 squared is 0. 1 squared is 1. Okay, at x equals 0, open or closed? Closed, just close it. At x equals 1, closed again. What shape is this, guys? Parabola. So just make it curved. Okay?
So you just do that like 1 point, you can't go out more?
Nope. It doesn't live. That's all the roommates gave that function. Like, it really got the short end of the stick. Right? Yeah. So then, starting with the next one, the function is just y equals 1. It's just a horizontal line. So at x equals 1, it's 1. And then it just goes like this. Just a horizontal line. Okay. When you're graphing these at home, ruler, graph paper. Otherwise, if it's not on graph paper, there is no credit. You've seen that already. Okay. Yep.
Do you want us to graph in different colors?
It's up. No, you don't have to do that. I do it like that so you guys could see, but you don't have to do that. Okay. Here we have to write the equations for this. Okay. So again, I have 1, 2, 3 functions. Okay. These are linear equations, all right? You know how to write linear equations since you were little. You need a slope and a point, and a y-intercept, rather. So for the first one, what's the slope? Positive a half, up 1 over 2. What's the y-intercept? 0. So the first equation, y is half x plus 0. Second equation, what's the slope? Negative 2. Down 2 over 1, negative 2. What's the y-intercept? 2. So that's y equals negative 2x plus 2. So far it's algebra 1, pre-algebra. 3, what's the equation to that one? Y equals what? It's a horizontal line at negative 1.
0.
Y equals negative 1, because of, right, it's a horizontal line at negative 1.
Oh, if it was on like the line.
Right, so slope is 0, right? Yeah. Okay, so now we're going to build our function. F of x is equal to, and the curly bracket. We're going to put each of the functions without the y's, okay? First function is half x, comma. Where does it live? From negative 2 to 0, right? X equals negative 2 to 0. This is the only time where we're going to do it algebra 2 style. Closed circles gets the, those inequalities. Second function is negative 2x plus 2. Where does that live? From what to what? 0 to 1. But look, it's open at 0, closed at 1. Third function is just negative 1, and it lives from 1 to 3. 1 is open, 3. One last thing, and then I'll take your question. Look at this at the 0. You see here at the 0, this is closed, this is open. You cannot have both closed at a point. So it can't include the 0 here and here, then it won't be a function. It can't include the 1 here and here, then it won't be a function. It can, however, be open for both at the same point. It just can't be closed for both. Okay, yeah.
Why are we writing it like in the old and the algorithm?